Okay, time to do some practice for finding those tangent lines and derivatives at a point in particular. Now, of course, we want to do practice because the more practice we do, the better we get. And we're going to be awesome. I mean, we're going to be amazing. We already are amazing. You're going to be amazinger and possibly someday the most amazingest. But okay, but in the meantime, we got to do the practice. And that means do as much of the problems as you can on your own before looking at the solutions. Make frequent use of that pause button. You might watch some of it only to help you get going or to help you get unstuck. And remember, the more that you do, the better you are. All right, let's get going. So the first problem. Given y equals 3x minus 7 is tangent to y equals f of x at x equals 4, find f of 4 and f prime of 4. All right, well, this one is going to be a really quick problem because it's just a little quick reminder. Hey, do you understand that tangent lines are storing information? And so we know our basic idea is if I have the tangent to f of x at x equals a, really that's just saying, hey, I can tell you what is the function at a and what is the derivative of the function at a. And the way to do that is to think about where these things show up. So the slope of the tangent line, that's the rate of change of the tangent line, which is the rate of change of the function. That's what's being stored in our derivative. So I say, hey, I can see the slope, that's 3, so that tells me f prime of 4 is equal to 3. All right, that was pretty quick. Aha, so maybe the 7 is f of a? Whoa, 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 slow down there, my friend. Slow down there. What's going on for f of a? Well, this is where the word tangent comes in. Tangent says we're touching. We're touching the function at a. So if we were to plug in 4, so really this is where our a is at 4. So if we plug 4 into this function, that would be what the tangent line does at 4, but it's also what the function does at 4. So 3 times 4 minus 7. 12 minus 7. 5. Good. So f prime of 4 is equal to 5. And that's it. There's our answer. We're done. Done. Ah, what a fun problem. What a fun problem. All right. Well, now, another question. Suppose our function is the absolute value of x. What is the derivative at 0? All right. Well, we've learned about the notation for derivatives. So we know that f prime of a, in our case, f prime of 0, would be the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. That's just the definition. That is what f prime of 0 is. Well, let's clean it up. So this is h. 0 plus h is h. And so if I plug h into my function, what will I get? I'm going to get the absolute value of h. Then plug 0 into a function, absolute value of 0 is 0. And then downstairs we get absolute value of h over h. Now, it's a little bit dicey here because we have absolute value, which means there are slightly different behaviors depending upon whether h is positive or negative. So let's split it. If we go from below, so h goes to 0 from below, and we take this limit of absolute value of h over h, well, it's really the same. Because I'm coming from below, h is a negative number. So when I take the absolute value, I need to correct for its negativity, which means it'll be negative h over h, which means this is really the limit as h goes to 0 from below of negative 1, which is negative 1. All right, limit as h goes to 0 from above. Okay, now in this case, because I'm from above, that means I'm positive. I'm a little bit above 0. So here's 0, and I'm a little bit above 0. I'm over here. I'm on the positive side. So the absolute value just says, this number is fine as is. No need to make any changes. So this becomes the limit as h goes to 0 from above. H over h, that's the limit as h goes to 0 from above of 1, which is 1. Now, we look at this and say, Now, why are we saying, Well, you'll see that when we approach from the two different sides, we got two different answers. These don't match. Well, what does that tell us about our limit? It tells us our limit does not exist. We can't find it. Now, let's pause and think about what this is telling us about the absolute value function. So let's think about what the absolute value function looks like. So if you were to sketch the absolute value function, it's pretty easy to sketch what it looks like. It looks like a V. So here's the shape. Now, the notion of limits is the idea, let's get closer and closer and closer. So let's do that. So I'm going to zoom in. So if I zoom in, what happens? Well, when I zoom in, I'm going to look like that. Okay, well, let me zoom in some more. And if I zoom in, what's going to happen? Well, I'm going to look like that. Okay, well, let me zoom in some more. In fact, this time I'm going to zoom in really, really close. So that's a very, very tiny. I'm zooming in a lot at this stage. And when I do that, what do I see? All right, I see that that's getting confusing. There are so many lines here. So let me just highlight. So here's my absolute value. Here's my absolute value. Here's my absolute value. Notice every time I zoomed in, what happened is I kept looking not flat. There's always that sort of right there. And no matter how far I zoom in, that doesn't go away. It never becomes a line. Well, since it's not a line, if when I zoom in, that says I can't talk about the slope of it. And that's why we say there's no derivative, because the local behavior of the function at that point is that there's no flat line that it's mimicking. All right. So it's possible that a function may not have a derivative. Really, it's possible it might not have a derivative anywhere. But here, at least, there's at one point. Now, you might say, okay, well, what if you weren't at 0? What can we say? Now, in this case, it's actually super easy. In fact, we can do the derivative without doing any limits at all. Because think about what our function is. And again, we'll give a quick sketch. When we look at our function, the question is, well, what's the best line that approximates it? So if I'm positive, if I'm over here, so let's say I'm looking at that piece right there. Well, I can cover this stuff up, and I say, well, what's the best line that approximates that? Well, the thing is, it's already a line. So the best line which approximates it is that line. So this follows the line y equals x. So that tells us that our derivative here is equal to 1. On the other hand, suppose I were looking on the other side. So I was looking over, say, at this part. Again, I only need to know the local behavior. So even though far away it's doing something different, locally it's looking like a line, it's behaving like a line. And so I can say, well, the derivative is the slope of that line. This is the line y equals minus x. And therefore, the derivative on the left-hand side is negative 1. So in essence, the derivative is either negative 1 or it's positive 1. It just depends on which side we're on. And, well, then 0 is then that uncomfortable transition stage. So, all right. So that is that problem. All right. Good. Good. Okay. Find the tangent line to y equals 1 over root x at x equals 4. So, to get a tangent line, well, really, whenever we see the word find a line, it says, hey, I'm after two pieces of information. I need to know a point, and I need to know a slope. Now, the point is almost always the easier thing to find. In our case, we know the x-coordinate is 4, so that's good news for us, 4. To get the y-coordinate, I can plug it into the function. 1 over the square root of 4? Well, that would be 1 over 2, a half. Okay, woohoo, we're halfway there. Woo! Granted, we probably just did the easier half, but still, we're halfway there. Woo! All right, we have to celebrate our victories when we can. Now let's talk about our slope. So the slope we'll get from the derivative. All right, let's do it. Okay, I suspect it might take us a little bit of work. That's all right. We don't mind a little bit of work. So the slope will be the derivative at 4. So right now, we don't have many tools for finding the derivative, so we're going to go and do it by the definition. So we have the limit as h goes to 0 of f of 4 plus h minus f of 4 all over h. Remember, we prefer the definition of limit that involves the h going to 0, because it's going to be a little bit easier for us to extract the cancellation. So far, what I've done is I've written down essentially the definition where I've put in a equals 4. Okay, so this is the limit as h goes to 0 of, now I'm going to plug 4 plus h into the function. So 4 plus h into this function. So that says, so see this function right here, we've written as y equals, really this is our f of x. So wherever I see an x, I'm going to replace it by 4 plus h. So 1 over square root 4 plus h. Then minus 1 over square root of 4 all over h. Okay, good. Now we start thinking, okay, we're ignoring where this limit came from. Now we have a limit. How do we handle this? We know as we start that when we're dealing with limits that represent derivatives, it's automatically going to be a 0 over 0. We don't even need to bother checking. We know there's going to be more work. There's always more work when it comes to derivatives. So we start thinking, okay, what are some things we can do to help us do the work? Well, we see that there's a difference upstairs of fractions. So the natural thing to start by doing is to say, let's put these together. So in other words, we're going to get a common denominator. So upstairs, well, the common denominator would be what you would get when you multiplied them together. So that says our common denominator is the square root of 4 plus h and the square root of 4 multiplied together. The first term you'd have to multiply square root of 4. The second term you'd have to multiply by square root of 4 plus h. So in other words, when I say multiply by square root of 4, I mean by square root of 4 over square root of 4. Here, square root of 4 plus h over square root of 4 plus h. Don't forget there's an over h here. Now, the way I'm going to do that is I'm just going to move it up here as a 1 over h, just because I don't like fractions within fractions. It doesn't look too pleasant, and it's a little bit more tedious to write. All right, so that's what we have. All right, good. Progress. We still have 0 over 0 because there hasn't been any cancellation. Until there's cancellation, you haven't gotten rid of your problems yet. So, the next step. Well, up here is, we see a 0, which is a little bit more subtle. See, here, this 1 over h, that's a blatant 0 down in your denominator. It's like, hey, look at my 0-ness. I'm very 0. So we want to get rid of the 0 here. In other words, we want to find something to extract the h. So, how do we get there? Well, we'd like to get it out of the square root. How do we get things out of square roots? We conjugate. So, we're going to multiply by square root of 4 plus square root of 4 plus h. And we're going to do it both upstairs and downstairs. All right. Good. So, what do we have? Well, we're going to have, you can ignore the 1, because times 1 doesn't change anything, a squared minus b squared. So, 4 minus 4 plus h. Notice the parentheses. Parentheses are your friends. They make sure you don't forget anything, like a sign. You don't want to forget that. That would be terrible. We want to make sure we keep everything. We want to get the full and correct answer. All right, so square root of 4 plus h times square root of 4 times an h times, and you don't expand this. You just leave this as square root of 4 plus square root of 4 plus h. Now, here's where we start saying, all right, if we've lived a good, clean calculus life, nice things should happen. Not really a good, clean calculus, good, clean algebra life. This is really algebra that's happening at this stage. What's nice? The 4's cancel. See, there's a 4, subtract a 4, which means that this upstairs part really is minus h. Don't forget that minus sign. And I say, hey, wait a second, there's an h up and an h down. Those cancel. We've succeeded in canceling off something which was causing zeros. So this is a moment to be like, woohoo! Yeah, we got the cancellation! If you're doing a test, you should be quietly. But still, you should be excited. It's like, I'm making progress. I'm doing it. All right, so we have limit as h goes to 0, upstairs, minus 1. Don't forget that minus sign. Downstairs, square root of 4 plus h, square root of 4, then square root of 4 plus square root of 4 plus h. And now, the next thing, I'm almost off the screen. Sorry about that. The next thing is plug in h equals 0. Because once you've done some cancellation, now is a good time to say, let's see if we get a number. And if we do, that's the number. So this is what? Upstairs, negative 1. Downstairs, we have a square root of 4, because the h goes to 0. Square root of 4 times square root of 4 plus square root of 4. Or if you like, this is 2 times 2. This is 2 plus 2. 2 plus 2 makes this 4. So I have 2 times 4, which would be a grand total of 16. 2 times 2 times 4. Good. Great, even. Okay, now, what is that? Well, that's not our answer. I know you're like, wait, we just did a lot of work. Shouldn't that be our answer? Haven't we done enough? But remember, what did we find? What we found is f prime of 4. What were we looking for? We're looking for a line. That's not a line. You always have to remember, what is it we were looking for? But it's an important part to get to our final answer. You see, our final answer is going to be a line, and we needed this to get the slope of our line. Now with our pieces in place, we're ready to write down our answer. So I like the format y equals the y value, so that's 1/2, plus the derivative, minus 1 over 16, times x minus the xi. So in other words, this is your y equals f of a plus f prime of a times x minus a. Write in whichever format you feel comfortable doing, as long as you get it. And this is great. Now you may say, do I need to simplify? Well, it just depends. It depends on what you're doing and what your instructions have been. A good rule of thumb is always follow instructions. So if instructions say simplify, then you should follow those instructions because you want to make sure you get all the appropriate points for your work. If it doesn't, well, just give a correct answer. And sometimes there's more than one correct way to write your answer. All right. Let's do another one. Another find a tangent line. Okay, well, we know how to find tangent lines. Hopefully we're going to get pretty good at this. So when we're talking tangent lines, we need to talk about our point, and we need to talk about our slope. So we know our x-coordinate is 0. All right, what's our y-coordinate? Well, plug 0 into your function. Sine of 0 is 0. Okay, well, that's pretty good. How about our slope? All right, well, slope means derivative. So we're going to look for our f prime of 0, where the f is the sine of 4x. So that's our limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. If you're using the limit definition of derivative, one of the best things to do on the first step is to actually write down the definition, because you're like, okay, I know what I'm doing. I've got the definition. So now we're going to replace our inside, we're going to plug it into our function. So limit as h goes to 0, plug h in, we'll get sine of 4h minus f of 0. Well, we already computed f of 0 to be 0 all over h. All right, good. Now, at this point, we might be saying, hey, this feels familiar. Well, yeah. You see, recall that there's this nice basic rule that says sine of blah over blah goes to 1 if we take the limit as blah goes to 0. So we see we're kind of in that setting. We have sine of something for h over, well, it's not quite the same thing downstairs. Not yet. But if it were, then we could pull this fact out. So how do we make this look like the inside? Well, the only difference is there's missing a 4 downstairs. Well, that's easy to fix. We put a 4 here. Now, we can't just put a single 4 by itself. We've got to compensate. So if I put a 4 downstairs, I'm going to put a 4 upstairs. These 4's cancel out. But now I say, hey, wait a second. The inside part of the sine matches with what's underneath. And the 4h is going to go to 0. Because that's, see, h is going to 0, so 4 times h is going to 0. So this full first part, the sine of 4h over 4h, that full expression goes to 1. And of course, the 4 is going to go to 4. It's actually already at 4. So we get 4. Aha! Aha! That's our slope. Good. Good. Progress. Progress. Now, what comes next? Well, we have our point, we have our slope, and therefore we can say our line. Well, y equals our y value, 0, plus 4 times x minus our x value, 0. Well, I think this is a reasonable time to say, hey, I can simplify that. Y equals 4x. And that's our line. Good. Woohoo! Nice. Now, we did have to sort of somewhat hope that we had at 0. If we move away from 0, things get a little bit dicey here. And so we're going to have to say, well, what happens? That's a great question. And we're going to get to that in a couple of sessions. So don't worry. We're going to be able to take the derivatives of things like sine at places other than 0. It's coming. It's coming. Don't worry. We'll get there. Be patient. Be patient. All right. So, here we go. Next problem. So let's just do sort of a nice general statement. Suppose I have the quadratic function. So I have c, d, and e are constants. And I'm not going to specify them. They're just some arbitrary constants. So, but it's cx squared plus dx plus e. And now I want to find the derivative at a for any a. So I just, essentially I'm after the slopes of tangent lines for parabolas. So this is going to be good for some of our more fun problems that we're going to practice on. So let's just work through it. So f prime of a, according to our definition, that's the limit as h goes to 0 of f of a plus h minus f of a all over h. Definition. Good place to start. Equals the limit as h goes to 0. Now, I'm plugging in a plus h. So everywhere where I currently see an x, I'm going to replace that x by a plus h. So c times a plus h squared plus d times a plus h plus e. That is my f of a plus h. Minus, Now I'm going to plug in a. C times a squared plus d times a plus e. All right. Now, notice my use of parentheses. I've put parentheses around the a plus h's. I'm putting parentheses here because of the minus sign. Parentheses are important. And I'll point out that there's really a check that should happen in just a moment here. But you want to be careful because it's really easy to forget parentheses and then to forget things such as the fact that this minus is going to distribute through to all those pieces, or that this d is going to distribute through, and so forth and so on. So what do we have? This is the limit as h goes to 0 of c times, let's expand it out, a squared plus 2ah plus h squared plus, I'll go ahead and distribute dA plus dH plus E, distribute the minus through, minus CA squared minus dA minus E all over H, which is the limit as H goes to 0 of CA squared plus 2 times C times A times H plus CH squared plus D times A plus D times H plus E minus CA squared minus D times A minus E all over H. All right, now what's the check? The check is that things should cancel. And in essence, what should happen is if we run our cancellation, so there's CA squared cancels with minus CA squared, DA cancels with minus DA, plus E cancels with minus E. If cancellation isn't happening, something went awry. It needs to be fixed. Now, notice that the terms that didn't cancel have something in common. They all involve H. That's another check. All the terms that are left over should have an H. Since they all have an H, I can factor that out. H, then 2 times C times A plus C times H plus D all over H. And now we're like, oh, we truly have lived a good life. The H's cancel. And now we're like, hey, our limit, it's beautiful. It's beautiful. It's beautiful. It's beautiful. It's true. Because there's no 0 over 0. So as H goes to 0, what happens? Well, the 2CA doesn't do anything. There's no H involved. The D doesn't do anything. There's no H involved. This C times H goes to 0, and therefore we get it's 2 times C times A plus D. Now, if you've seen calculus before, you're probably like, ugh, yeah, I knew that. It's so easy. You can just skip all this limit stuff. Why are you making it hard? And I totally feel you. I really understand how you feel. But we've got to start. We've got to go through the groundworks and lay the foundation. We are going to get to the point where this derivative is going to become one that we just write down without having to even think. My goodness, that's our goal, is to not have to think? Well, no. Our goal is to think about more fun stuff, more challenging problems. Before we leave, I just want to point something out. Notice that the C showed up in the answer, the D showed up in the answer, but the E, it vanished. Is that reasonable? And why? And the answer is it is reasonable. If you think about what the E is doing a movement like this. It's an up and down movement. Now, if I have a line, imagine this is a line. If I move it up and down, what happens to the slope of that line? The answer is the slope here is the slope there is the slope there. And therefore, the slope doesn't change, which means the derivative doesn't change. All right, good. All right, let's do one more for this round. Okay. So we're given the parabola y equals x squared minus 3x plus 4, and we're given a line y equals 3x plus 7. We want to find all tangent lines to the parabola which are parallel to the given line, and also find all tangent lines which are perpendicular to the given line. All right, so this is a good time to remind ourselves what various things mean. So we have two words we have to focus on. There's this word parallel, and there's this word perpendicular. So let's start with parallel. So two lines are parallel if what? They have the same slope. So in other words, these run together. On sort of a fun side note, well, because, hey, we like fun side notes. Have you ever thought about the equal sign? And you're probably like, no. I mean, that's what it is, right? It's an equal sign. But why is it the equal sign? Why does that symbol denote equals? What was the thought process? Well, the thought process was they were like, well, what can we draw that represents two things which are equal? And the idea was, and if you go back and look in really old textbooks, you'll sometimes see equal signs that look like this. They're very stretched out. And what they were is it's two sets of parallel lines, because the thought was, what can be more equal than two parallel lines? And so when you're drawing little equal signs, you're drawing two parallel lines. Aha. All right. Anyway, sorry. Back to the business at hand. Now, that's parallel. Perpendicular, well, that's a little bit more complicated. So perpendicular equals negative reciprocals slopes. Well, that sounds complicated, but what it means, if one of the slopes is m, then the other slope is minus 1 over m. So the negative, and then the reciprocal means flip it over. Now, what do we have? Well, we have our parabola and we have our line. So let's look at our line. Y equals 3x plus 7. Our slope is 3, which means if we want to be parallel, what we need is to have our slope of our tangent line be 3. So our goal is, where does our tangent line have a slope of 3? Now, this is a quadratic. The nice thing is we actually know how to find the slopes of quadratics. We just did it. And so parallel, we need to have slope of 3. And if we want to say about the slope equals 3, that means f prime at some point equals 3. And now, well, f prime of a would be, if we follow the rule, it would be 2 times 1 times a minus 3. So we need to have 2a minus 3 equals 3. Now, that tells us that if we're parallel, we need to have a equals 3. So this is the, when we talk about the a equals 3, this is the x-coordinate of tangency. So in other words, we haven't found the tangent line, but we found where to take the tangent line. In other words, we should take it at x equals 3. All right, so how does that help us finish our answer for parallel? So let's say this is the parallel. Well, we need to know the y-coordinate. So let's say plug in 3. 9 minus 9 plus 4. So we could say y minus the y value, y minus 4, is equal to our slope. Well, we know our slope is 3 times x minus the x-coordinate, and that's what we found here. So it's x minus 3. All right, so that was our parallel. Now, perpendicular. Okay, so perpendicular, what would that be? Well, it takes us a little bit longer. It's a bigger word. Probably gets you more points than Scrabble. Okay, that says we need the slope to be the negative reciprocal, so minus a third. All right, now other than that, really the procedure is much the same. That says we need the derivative to be minus a third, which says we need 2a minus 3 equals minus a third. And this is the part that's a little bit more sensitive because it's going to take us a little bit more work. We could almost just read that and be like, oh yeah, that's a equals 3. Here, I don't think we could just do that. So let's start by rearranging. So we add 3. So you get to 3 minus 1/3. Well, 3 is 9/3. If I take 9/3 and I subtract 1/3, that would be really 8/3. So 2 times A is 8/3, which says that A is 4/3. Okay, so again, what have we found? We found where we should take our tangency. So this is the x-coordinate of tangency. All right, well, it's something. It's something. So our perpendicular, we have y minus something is equal to negative 1/3, because our slope has to be negative 1/3, then x minus 4/3. But we're not done, because we need to say what goes here. Well, plug it in. Okay, so plug it in, we'll have 4/3 squared minus 3 times 4/3 plus 4. Now the good news is, see, look at this. The 3's cancel. Boo, boo. Minus 4 plus 4. More cancellation. Pew, pew. You don't actually have to make the pew sounds, but doesn't it feel good? It makes it more fun. And don't you want to have fun when you're doing math? No, you don't even have to answer that. I already know, though. Of course you want to have fun doing math. Ha, 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 ha. All right, which means our y-coordinate is 16/9. So that goes as y minus 16/9. That what goes there. And now we're done. We found them all. In this case, there was only one that was parallel and only one that was perpendicular. Now, it can be the case, depending on the function, you might have several. But the key thing is just to work the process, and you can do that. By the way, I do want to mention that there is a word that you'll start hearing, especially once you get into Calculus 3. So we might as well sort of plant the seeds so we can start harvesting them later on. So that is, when you see this word perpendicular, you might also see it sometimes written as a normal. So you have something called the tangent line, but you also have something called the normal line. And what is that? Well, if I think of, let's say, like a parabola, then if I have a tangent line, so the tangent line is something which looks vaguely like this. Here's my tangent line. The normal line is something which looks like this. It passes through the point, but it's perpendicular to what the tangent line is doing. So if you ever see something that says, hey, find the normal line to the curve at this point, it says, oh, take your tangent line and then find the perpendicular line that also runs through that point. So that's what normal means. All right. Well, good. Good practice. Good practice. Keep it up.